Hello everybody, welcome to today's session. Uh, we'll be discussing a topic from waves basically, or what I would call superposition of waves. So whatever we discussed today, the phenomena, the concepts are actually arising from something which I'll tell you right now. If you have a wave which propagates in this manner, like in this direction, similarly if you have another wave which propagates in the opposite direction. So what do you mean by wave motion? Like how does a wave move? In fact, there's nothing which is moving actually in the forward direction. What happens is there are particles which go up and down. So like they go up and down alternatively. So if you sketch their shape now, and then right after maybe a small instance when they change positions and you sketch them. So if you keep taking a picture or you keep sketching the positions of the particles, it will feel as if the wave is moving in the forward direction, but there's nothing which is actually moving. So nevertheless, we can just visualize it in the form of motion. So if you have a wave which like apparently is moving in the forward direction and the other wave from the other side is moving in the opposite direction, they superimpose. What do you mean by this term? Superimpose. Superimpose means basically a particle. What do you mean by wave actually? Wave is nothing but a disturbance in the medium. So the first wave is the first disturbance, and this particle will move according to the disturbance, whatever the equation of the disturbance is. Similarly, from the other side, there is another disturbance coming. So, if you sketch the position of this particle with respect to first disturbance and then with respect to second disturbance and then just add the positions, you'll get the net position. That is called superimposition. So what happens here is these are nothing but particles on the wave which are actually moving up and down, and then similarly here. So the up and down motion will give you the equation of the disturbance. So if you take this particle and take this as the first disturbance, take this as the second disturbance, add positions with respect to each disturbance, and then calculate positions with respect to each disturbance and then just add the positions, you'll get the net position, which is nothing but y1 plus y2. Let y1 be the position with respect to first disturbance, y2 be the position with respect to second disturbance. So what will happen is once they superimpose, it will feel as if uh, there are standing waves formed. So standing waves, which I will just tell you what they are, is nothing but uh, uh, what do you say? An outcome of superimposition of waves. So don't get confused with the heading of the video. The heading of the video says harmonics on a stretch medium, and then I'm explaining you the formation of standing waves right now, and then we'll just uh, discuss how standing waves are formed on a string. So a string is nothing but a stretched medium. And what I mean by harmonics is something like this. If you have a string completely going up and down, or if you have a string which is forming two loops, right? So you can imagine if you pluck the string from the middle, there will be one part of the string, it will feel as if there are two loops which are formed in the string. Similarly, if you plug the string at a relevant position, you can also get three loops. So these are called harmonics. Like just one loop is called first harmonic, two loops are called second harmonic, and three loops are called third harmonic, and so on. Like for a string which is stretched from both sides. So This is essentially a result of formation of standing waves only, and standing waves are a result of superimposition of waves. So that's why I'm going in that manner. So what you have to understand is, if there are, so how is a wave equation? It's written in this form: y is equals to a1 sine kx minus omega t. Let this be your first wave. If you have a minus sign in the middle, that means your wave is going in like from left to right. Like that's how it's. I'm not going into the derivation of that, but that's how it is. Let us just discuss the relevant concepts alongside this. Yeah. And similarly, if you have a plus sign in the middle, the answer is opposite. Like your wave moves from right to left. So I can have this. Let this be the first wave, and let that this be its equation. Let the equation of the second wave be a2 sine kx plus omega t. So let them move in opposite directions. So if I take a random particle, uh, I hope you understand what this wave equation means. For a particular x at a particular time, I'll get y. That means there are various particles in the medium. The x coordinate of the particle can be thought of its roll number as something like the roll number of the particle, right? And time is something which basically let at from time equal to t equal to 0, whatever the time is measured, let that time be t. So how do I get the position of this particle with respect to time? So first I'll have to come to the particle. For that I'll put its x coordinate, and at what time do I need the position? For that I'll put the time. So basically there are two variables here, x and t, right? So similarly now I'll pick up a random particle. I'll put its x coordinate and the required time in this equation, in the first equation. So I'll get the position y with respect to this disturbance. Similarly, I'll put the same x coordinate in the second equation, and the same time I'll get this. Let this be y1. I'll get the position y2 with respect to this disturbance, and then ultimately I'll just add y is equals to y1 plus y2. Right. So for that you'll just have to add these two trigonometrically. Basically just add them and apply some trigonometry, which I'm not discussing in detail. I'm just going into the concepts of this. So what you have to understand is, I'll somehow just extend this to what is relevant to us for this stretched medium part. So in a stretched medium, let me just clear some space. So I hope you understood what I was trying to mean. Just calculate individual y's and just add them up to get the net y. So now what we'll do is we'll understand how all of this happens on a string. So until now I was discussing air, maybe something like a gaseous medium, but how about a string? So in a string which is stretched, the velocity of the wave, so what happens is, for example, if there is any oscillator which is put somewhere close to, like somewhere on the string, and the string is oscillated, the velocity of the wave is given by this formula, under root t by mu. And once again, I'm not deriving this formula as to how I've got this. You just have to remember it. What is t here? T is the tension in the string. What do you mean by tension? If I pull the string from both sides with a force F, the tension in the string is F, right? So that is what tension is. What is mu? Mu is nothing but, let the mass of the string be m and let its length be L. So m by L is nothing but mu, which is mass per unit length. So it's under root tension by mass per unit length. And don't go into the derivation of this formula, just have to remember it as it is. What is V here? If I put an oscillator and start sending waves through the oscillator, the velocity with which the wave will travel is nothing but this, under root t by mu, right? So this is what it is. Now what you have to understand is, if I randomly pluck the string somewhere, or if I randomly put an oscillator somewhere, I'm not going to get the loops that I was talking about. And there are reasons to why that happens, because it's something like this. When I take the string and I pluck it at the center, then the string oscillates in a proper manner, right? You can see loops which are being formed. Because what happens in the string also is, there are waves which are sent from one side, they get reflected from the other end, and there are basically waves from the other end. So like how it goes is, the waves first go from along the string in one direction, they get reflected at the rigid boundary, they come back and they interfere with the waves which are coming from the opposite side. So that is the reason why standing waves are formed. Now standing waves will properly be formed and it will give a resonant frequency only when the string is plucked at the right points. What do you mean by resonant frequencies? Resonant frequencies are frequencies where you'll get loops like this. So basically your string will fully oscillate, or it will oscillate in 2 loops, or it oscillates in 3 loops. These are called resonant frequencies, and you will get them only if you pluck them at particular positions, like if you put the oscillator at a particular position. So here maybe if if you randomly just put an oscillator at some position which doesn't give rise to the resonant frequency, the oscillations will just die out. Like the string will randomly just give some motion and the oscillations will die out. But it will resonate in this form if it is plucked at relevant points. And that is what we have to calculate, right? That is the phenomena. Why is this phenomena occurring? Because of the formation of standing waves. And why is standing waves occurring? Because of the phenomena of superposition of the waves which go in a certain direction and get reflected from the rigid body, like the interference of these two waves. So let's discuss how it all goes now. So look at this frequency, look at this particular loop. So here you just have one loop. Now remember, in a what do you say, standing waves, these are all standing waves basically. So in standing waves, what happens is, there are points which don't move from their position at all. They are called nodes. And there are points which go to the highest amplitude, like all of them only go to this much, but this point goes to the highest amplitude and it's called an antinode. Similarly here, these are your nodes because they don't move at all, and in the middle you have antinodes. Similarly here, this is a node, this is a node, this one is a node, and this one is a node. Like nodes don't move from their positions, and these are all your antinodes, like in between the nodes. So with this understanding, I would like to tell you if I go from a node to an antinode, I cover a lambda by 4 distance. Like the wavelength is nothing but basically whatever the wave was formed, 1/4 of that wavelength is a distance from a node to an antinode, right? Similarly, if I go from a node to a node, so node to an antinode is lambda by 4, antinode to a node is again lambda by 4. So node to node, basically this particular uh, length is nothing but lambda by 2, right? And if you go from one node to another node to another node, you get a complete lambda. Remember this principle in mind, right? So keeping this in mind now, coming to this particular diagram, the first frequency, the the first harmonic or the fundamental frequency, it is called first harmonic or fundamental frequency. Here, as you can see, the length of the string, I go from a node to an antinode to a node. So I go from a node to a node. That means lambda by 2 is the distance, this particular distance, and this is also the length of the string. So I can say lambda by 2 is the length of the string, right? Remember from wave theory, from basic wave theory, lambda times frequency is nothing but the velocity of the wave, right? So lambda times frequency is nothing but the velocity of the wave. So I can simply say the frequency of the wave is nothing but velocity of wave by lambda, right? It's nothing but this. So if I want the corresponding frequency to this, so corresponding fundamental frequency is what I want, then what I'll simply do is I'll put lambda is equals to 2L, and lambda is nothing but V by F from this. So V by F is nothing but 2L. So I can say F is nothing but V by 2L, which is, and V is nothing but under root T by mu, like the tension which the string is put under, divided by its mass per unit length and the square root taken. So it's nothing but 1 by 2L into under root T by mu. This is nothing but the fundamental frequency. Similarly, coming to the other frequencies, I'll have to create some space. So the second, so what you initially had was a fundamental frequency, which was nothing but like this, for which we saw, like this was your string, and the fundamental frequency was something like this, for which we saw that our frequency, fundamental frequency, was 1 by 2L into under root T by mu. For the second case, like the second harmonic, you have two loops, right? So when you have two loops, basically you are going from a node to an antinode to a node again, right? So if you look at this, this entire thing is the length of the string. Remember, at one instance of time, the string is only like this. At the second instance, the string is like this. At the third instance, the string is like this again. So it happens so quickly that it seems to you that there are loops formed. But basically, there is just one string, right? So it can't happen that this and this are formed together at the same time. That's not possible because you just have one string. So it takes a sinusoidal shape, and at the very next instant, it takes a sinusoidal shape in this manner, and it happens so quickly, this transition, that it feels as if there are loops. So you go from a node to a node, that's why the distance that you cover is nothing but lambda. And lambda here will be the length of the string, because this entire thing is the length of the string, right? So lambda is equals to L. Lambda was nothing but, like from the previous case, we had lambda times F is equals to velocity. So we have lambda is equals to velocity by frequency, and that's L. So I can say, and now this frequency is the second harmonic frequency, right? This was your first, or so first harmonic or fundamental, and this is second harmonic. So F is nothing but V by L. V is nothing but under root T by mu into 1 by L, right? So you can see that second harmonic is twice as much as fundamental, right? Because this is 1 by 2L into under root 2 by mu F fundamental. This is 1 by 2L into under root 2 by mu. This is 1 by L into under root 2 by T by mu, right? Similarly, what if you have n loops on a stretched string? So like if there are n loops, how do I find the general expression for the nth frequency or the nth harmonic, right? Also remember, second harmonic is also called first overtone, and the fundamental frequency cannot be written in terms of overtone, because overtones means anything which is above fundamental. So you have fundamental, first harmonic, then you have second harmonic is called first overtone, then you have third harmonic is called second overtone, and it goes like that, right? So this is in this manner. So remember, each loop is of a length lambda by 4, lambda by 2, because you're going from a node to node for each loop. If there are n loops, that means you're covering a length of n lambda by 2. And this entire thing is basically on your string. So n lambda by 2 is the length of the string, right? So if there are n loops, let that frequency be the fnth frequency, right? That's nth harmonic. So fn. So similarly, like n by 2 into lambda can be replaced by v by fn is equals to L. So nth harmonic frequency is nothing but n by 2L into v, which is under root T by mu. So from this you'll get all expression. If you put n equal to 1, you'll get fundamental frequency. If you put n equal to 2, you'll get this second harmonic or first overtone. N equal to 3, 4, and so on. It just goes like that. So this is basically the phenomena of waves, normal modes of a string. That's what it's called. So how do you know where to pluck, basically? So you always pluck at an antinode. First of all, remember, your string will be in resonant modes. What do you mean by resonant modes? Resonant modes means these particular phenomena, like first one loop, two loops, three loops, n loops. Whenever there are loops from, it's called a resonant frequency. They will occur only if your frequency is either f fundamental or f first harmonic or f nth harmonic. Like they have to be of this form. Your oscillator which oscillates the string has to have a frequency of this form. If it has anything other than this, that means your n has to be an integer here, because your length of the string is fixed, t is fixed, mu is fixed, n is what is changing. So basically your frequency of the oscillator has to be an integral multiple of 1 by 2L into under root 2 by mu, like into n. So this n has to be an integer. If it's not an integer, then you will not get these resonant modes. Like the oscillations will just dampen, they'll die out. They'll not take this shape. That's what you have to understand. And how do you know where to pluck for this to occur? So you always pluck at an antinode, because the place where you pluck goes to the highest amplitude, and antinode goes to the highest amplitude. So for the first fundamental frequency, you will pluck it at the center. For the second one, basically this is your center. This is the center between this and this, center between this and this. So you will take this to the antinode, take this to the antinode. Your string will take this shape, and then you leave it, right? Then it will oscillate in the harmonic frequency. So if you randomly pluck here and here, if you end up plucking here instead of exactly at the center, these oscillations will not occur, like they'll die out. So the frequency first of all has to be an integral multiple of this, and the plucking has to take place at relevant points for this kind of phenomena to occur. So I hope you have had a rough or a broad understanding now. So we'll now move on to discussing a few problems. So let me make some more space. Yeah. So the first question goes like this. In terms of T, mu, and L, find the frequency of A, fourth overtone mode, B, third harmonic. So it's a very straightforward problem, basically. Like there are no, it's pretty simple to go solve this. So what you'll have to first understand is if you understand what overtone and harmonic means. So remember, this was your fundamental frequency. This was your, this is your first harmonic, second harmonic. So these are harmonic and overtones. So second harmonic was your first overtone. Similarly, if you have three loops, this is your third harmonic and your second overtone. So whatever your overtone is, that plus one is your harmonic basically. So fourth overtone means, what do you mean by fourth overtone? It means that I'm talking about fifth uh, harmonic. So as we have already derived the expression for the nth frequency, so I need to find the frequency right in the question. So it's nothing but Fn is nothing but n by 2l into under root t by mu, right? And I need the fifth harmonic, that's basically my fourth overtone. So I need F5, and that's nothing but 5 by 2l into under root t by mu. If you're slightly confused about what this formula is, just go back to the theory and refer to it again. So coming to the third harmonic, again very very simple. Third harmonic is nothing but basically F3 is what you need. So F3 is nothing but given by this formula, 3 by 2l into under root t by mu. Right. So a very very simple problem. Just have to know what each term means, and that is the only slight challenge in this problem, I would say. So going to the next problem, slightly more conceptual. So what I'll do is I'll read the question and just draw the diagram and explain it to you rather than writing it completely. So the rodless mass BD, two strings, all right. Yeah. So here is a wall, AC, a ceiling maybe. There are two strings suspended like this, and there is a rod in the middle. Now from this rod, basically BC, so BD. So AB and CD are two strings, and BD is the rod here. This is D, right? So at a distance x from B, at a distance x from B, at a point P basically, I just attach a mass M, right? And then what I want to ensure is left wire is twice. So I need fundamental frequency of left wire to be twice the fundamental frequency of the right wire. That is the constraint. So find x. Yeah, how can we do this? That's the question. So it's not at all difficult actually. What you have to understand is the lengths of the strings are same. The fundamental frequency is given by this formula, 1 by 2L. So I'm just writing on the answer now. 1 by 2L into under root T by mu, right? The lengths of these two strings are same. The mu of these two strings are same because the strings are identical. I'm not mentioned in the question, but they are identical. So the only way I can have the fundamental frequency for these two strings different is that I have a different tension, right? So let the tension here be TAB. Let the tension here be TCD. So I need FAB, which is the left wire's fundamental frequency, to be twice the fundamental frequency of the right wire, which is CD. So I need FAB to be equal to 2FCD, right? So if I just put in FAB, or let me just make some space. So I can't really rewrite the problem. I hope you guys will remember it. We've got to FAB is equals to 2FCD, and we need to find out X. So I'll have to erase the question. So we were going in this manner. This was your ceiling. So this was the ceiling, and then you had two wires. You had a rod from here to here at a point X. You had a mass M attached. The length of the rod was, so remember this part is negligible. These two parts are negligible, like the rod is only this big. The rod is only this big. Forget this part. And the length of the rod is nothing but L. So like this length is L minus X. So this was AB string, this was CD string, and we came to the relation FAB is equals to 2FCD. As we already saw, FAB is nothing but 1 by 2L into under root TAB by mu AB, and this was 2 into 1 by 2L into under root TCD by mu CD. So you can cancel the 2L's, you can cancel the mu's also because they are the same. So Just the ratio of the tensions is what we have now. So tension in AB is equals to 4 times tension in CD. Right. This is what you have. There's one more thing that you have to take care of. That's nothing. That's actually, if you apply torque at this point, like this is a rod. So there is a force mg here, nothing but mg. There is a tension TAB which is pulling it in this direction. There is a tension TCD which is pulling it in this direction. But this rod is at rest, right? So the torque of all these three forces about this point has to be 0. So torque due to AB plus torque due to CD plus torque due to mg has to be 0. Right. So what you have to understand is torque due to mg will anyways be 0 because mg is the force which is passing through the point. So if you ever want to calculate a torque about a point, basically you'll have to take the line of action of force, calculate the perpendicular distance from the point and multiply that to the force. Like this is the tension. Let the magnitude of the tension be T. Let its line of action be this. It's at a perpendicular distance x from this point. So T into x is the torque. What if the line of action of force passes through the point? X will be 0, right? So that's why the torque will be 0. So torque due to mg will be 0. How about torque due to AB? Torque due to AB will be nothing but TAB into the perpendicular. So this is the line of action of force. Perpendicular distance from this point is nothing but x, right? So TAB into x is what you have. And plus torque due to CD will come with a negative sign and it will be TCD into, let this distance be L minus x. TCD into L minus x. Why am I putting a negative sign? Because remember torque is also a vector, right? So I'm not actually calculating the direction of torque here. You can use the cross product rule. Like torque is nothing but x bar cross TAB bar. If you take the cross product, you'll get torque in the inward direction for this and you'll get torque in the outward direction for this. So basically that's why there's a negative sign coming, because if this is TAB K cap, this will be TCD minus K cap. So this minus, I'm just writing it here like this and cancelling the K caps, right? So TAB into x is equals to TCD into L minus x is what you have. TAB is equals to 4 TCD into x is equals to TCD into L minus x. You can cancel the TCDs and then you have 5x is equals to L. So ultimately what you have is x is equals to L by 5. So if you place a mass at L by 5 distance, then the required condition in the question will be satisfied, right? So let's move on to the next problem then. This one is a nice problem again. And it goes like this. So you have, okay, 2 kg mass, fine. Okay. So you have a shape of this manner. Like a string passes through a fixed end over a pulley and is attached to a pan of mass 200 grams, and it also has a mass of 2 kg inside. Like there is a block of mass 2 kg which is placed in a pan of having a mass 200 grams, and this entire system is like taken over a pulley through a string, right? What happens is, when this string is plucked, when plucked, the string vibrates uh, at a fundamental frequency of 220 hertz. All right. Later, an unknown mass m is added, and the fundamental frequency changes to 260 hertz. Find m. So I hope you understood the problem. Initially, over the string, the string is taken over a pulley attached to the span of mass 200 kgs having a mass 2 kg inside, and then when it was plugged, the fundamental frequency that was detected was 220 hertz. Later, in the same pan, there was another additional mass of basically value m which was added, and then the fundamental frequency, like once again when the string was plugged, this part of the string, the fundamental frequency changes to 260 hertz, and from that they are asking us to calculate what m is. So once again, a very simple problem. So initially, you know, fundamental frequency is nothing but given by this formula, 1 by 2L into under root T by mu, right? So we are not given the length of the string, we are not even given mu. Remember, before adding the mass and after adding the mass, what is actually changing? So like, in fact, I won't even take, so like let F1 be the initial frequency, let F2 be the final frequency. So F1 is nothing but 220 hertz, and that is equals to 1 by 2 into the length of the string is L, like length of this string is nothing but L, into under root, let the tension here be T and mass per unit of the string be mu, or let the tension here be T1. Similarly, when new mass is added, the frequency changed to F2, that's 260 hertz, is equals to 1 by under root 2, 1 by 2 into the length of the string doesn't change even after adding the mass, because that's essentially the same, like between the pulley and the rigid surface, whatever the length is, that remains the same. Even the mu for the string doesn't change. What only changes is tension because of the addition of the mass. So I can say 220 by 260 is nothing but under root T1 by T2. Cancelling this, 2 11s are, 2 13s are. So I can say 121 by 169 is equals to T1 by T2. What is T1 essentially? Nothing but the weight that the string balances, right? So initially the weight that the string is balancing is nothing but 200, which is 0.2 kgs plus 2 kgs into g. mg is what it is balancing, so that's T1. After the mass was added, I had 0.2, which was the mass of the pan, plus 2 mass of the block, plus some additional mass m which was added into g. So just solving this, now you just have one equation and one unknown m, and from this you can obviously solve what m is yourself, right? So I won't go into that. Let me see if there is any other problem which is worth discussing. Hmm. So the rest of the problems that I can see in the book are almost similar to this formula. So everything is just based on this formula, 1 by 12 into under root t by mu. So we discussed three problems here, each of a different model, and all of this is just essentially telling you how to use this formula 1 by 12 into under root t by mu to proper importance. So uh, with this, I would like to conclude the session. I hope it was informative to you and this particular concept was clarified. So next time we'll come up with a different topic in mathematics mostly. So until then, see you. Thanks for joining.